Let me say share window and then share. Yeah, can you see it now?
Yes, we can.
Yeah. All right. Thank you for the opportunity. As introduced, I'm Sikelela Notununu. I'm from Safari. So my interest is in mathematical modeling. So I've been looking at uh, something called mathematical biology, which is also called epidemiology. So just to give you an idea of what I'm doing, I'll just use one of the work that I've done, which is on the effectiveness of quarantine as a measure to control the spread of COVID-19 in South Africa from mathematical modeling perspective. So here I'll just be giving you just a clue or just elaborating on what I've done. So here, first we have the outline, which I'm not going to go through, and then the introduction. So here I'm just explaining how COVID-19 is transmitted, the incubation period, and all of those things, as we all saw what was happening between, I think, 2019 and 2021, when we had COVID-19. So when it comes to mathematical modeling, what we try to do is that we try to take a real life situation, which can be any situation, and we try to put it in mathematical terms. So here, I modeled the COVID-19 problem using compartmental models, compartmental model, yes. So I had, in my model, I had susceptible, the exposed, infected, quarantine, and the recovered. So the whole idea here was just to see how effective quarantine is going to be in trying to lower down the spread of COVID-19. So as you all know, when we are doing mathematical modeling, we cannot just do it just like that. We need to have assumptions. So these are the assumptions I had, and then these were my parameters. And then now my main interest where I'm going to be explaining the model is here on how I come about the differential equation. So as I mentioned earlier, I have S, which is the healthy individuals. So if there is no one having COVID-19 within a midst, so that will mean that all of us are susceptible, we are healthy individuals. But now if an infected individual does come in, then now we're going to, some people, they might be exposed, those who might come to close contact, or sometimes, because we know that, for example, COVID-19, we can have direct and indirect transmission, meaning that someone can touch contaminated environments, which we do have models that consider that aspect of transmission also. But in this case, I was just considering the direct one, which is between human to human. So after exposure, when you start showing symptoms, we identify you as infected. This is a situation where you are able to, you become infectious, meaning you can infect others. And then from being infected, it's either you recover, or we take you to quarantine, or we also consider the disease-induced deaths, or you die. As you can see here, I have this box in arrows, meaning that these people, they're actually not contributing any further to the spread of the disease, even though we do have models where the dead individuals, they do contribute to the spread of the disease. As I said earlier, we can assume anything of our interest as long as it's going to make sense. So also, we also assume that there are natural death rates. As you can see that there is a mu going out of each and every compartment, meaning that from any compartment, except for this one, people can die naturally. And then due to the disease, it's only those in quarantine and those in the infected compartments who can die due to the disease. And then from recovery, people can also, from quarantine, people can also recover. So from that, we come up with this system of ODE, which governs the spread of COVID-19 with the assumptions that we have made. And then also one important thing, I'm not sure if, yeah, here it is. This is something that is called the force of infection. This is very much important. So what happens is that we try to see what compartments contribute to the spread. So in our case, as you can see from here, that the individuals in E and in I, they contribute to the spread because there is no controlled mobility in this model. For example, these ones in I can interact with the ones in S. And also these ones here in E, there are those who are also infectious in E. There are those who can transmit disease in E. So they also contribute to the spread of the disease. As you can see here on my force of infection, that the contribution is due to I and E. So this is the only proportion of the whole population that contribute to the spread. So this parameter here, I call it the modifying parameter because the contribution of I and E won't be the same. For example, the ones in I, all of them, they contribute to the spread, but the ones in E, not all of them to contribute to the spread. So from here, I was just showing the feasible region. As you can see, this is the proof for that, because we need a model that mathematically makes sense and biologically makes sense. So, and also, as you know, we need some sort of a domain that we'll be working in. So this is what I have here. And then also here, I was showing positivity. For example, we are dealing with a number of people. We cannot assume, or we have to show that these compartments, they are always going to be positive because we can never have negative number of people. So even there is that. And then here, there is something called the basic reproduction number. So this is just the average number of secondary infection that one infectious individual can produce. So this is very important when it comes to the analysis of the model. So I won't go through the calculation part. We use the next generation matrix to calculate this R0. So in our case, this is our R0, which is having two terms. As you can see from the schematic diagram I described, I was having two compartments to contribute to the spread, which shows that here we have two terms here. And then now these are the equilibrium points. So there is something called the disease-free equilibrium point where there is no disease, and also there is something called the endemic. So just to browse through, this was the disease-free equilibrium, and then now what is below here is the endemic equilibrium. And then we have stability analysis. So here we try to show it locally and globally. So locally, we mean that if the initial condition starts very close or starts in the neighborhood of the disease-free equilibrium, the solutions of the system will converge to the disease-free equilibrium. So that will be if R0 is less than 1. So this will mean that the disease is going to die out. And there's a case I'm going to explain there, which is something of interest nowadays. And then here, I use the Jacobian matrix to show that, because the idea was just to show that all the eigenvalues, they are having a negative real part. The eigenvalues of this Jacobian matrix taken at the disease-free equilibrium. So we were able to achieve that. And then we also showed for the endemic equilibrium. So here, remember, the idea is not to find the eigenvalues, was just to show the sign of their real part. So if we can come up with a condition, for example, if you use a disk and then you're able to show that the disk lie on the left, you see the XY axis, it lies on the left plane, on the left half plane, then you're able to show that the real part is negative. Also, that is enough to conclude. Hence here, I used a disk via the Gershgorin theorem together with the strict diagonal dominance. Then I was able to achieve that. And then, can I please jump a bit? So now here, this is global stability. So here, remember, this is for the disease-free equilibrium. What we're trying to show that is, irrespective of the initial number of infections we have, the disease can die out. That is global. Remember, in the local, I said, if we start in the neighborhood, now we are saying, if we start anywhere, the disease will die out. So here we showed that using the Lyapunov function. And then as you can see here that if R0 is less than 1, this guy here is going to be negative. So there are conditions here, which I might share the slide later if one is interested. Because of time, I will come here, which is sensitivity analysis. So here, with that R0, we're going to use it as our static output quantity, yes. So what we're trying to do, we're trying to see the percentage change that if now one parameter, so obvious that R0 depends on parameters as you saw there. So now we're trying to say to ourselves, what happens if there is a small change in one of the parameters? So the idea about sensitivity is that a parameter is going to be said to be sensitive. That is if a small change on that parameter results to a big change on R0. So to detect that, we're going to use the percentage change. So these signs here, as you can see, this one is positive for the psi and for the zeta and for the beta, which suggests that a small change in this one will result to a positive change on the R0, and these ones are negative. So there's the relationship of directly proportional and indirectly proportional. And then these are the numerical simulations. I'm going to jump them because of time. Then I'm going to go to the data because this was the main interest. So the data we use for this model, because we need to see if we can use the model to give advices to the policymakers. So we took our model and then we tried to fit it to the South African data. So this model does not talk about a vaccine or anything. So this data from Johns Hopkins University, and then we took it from the first day we had the first case of COVID-19 up until I think it was the 16th of February. Because on the 17th of February, we had the first dose of vaccine. So since this model does not talk about vaccine, we didn't take after the first day of vaccine. So we had that, and then it was difficult to fit the entire the first wave and the second wave. So what we did is that we took the data from here, the blue part, and also that. And then now this is the fit for the first wave, and that's the fit for the second wave. And then now, when we took the fitted values to substitute them to the formula of R0, we got our R0 to be this for the first wave and to be that for the second wave, which is too big. And the explanation to that will be there is a uncontrolled mobility. For example, then this model was too small. It was not capturing like a lot of most of the reality cases that one can think of, which is why we were having a very big R0 there. But in the improved model, which is what I'm working on now, where I'm having vaccine and I'm having some other assumptions that we can make, the R0 are really reduced. And then these are the fitted values for the first wave and the second wave. And then now this is discussion of the results we had. So this is just from the sensitivity analysis. And then now we're going to support this discussion using the fitted there. So you see, remember the idea was just to see the effectiveness of quarantine. But then we have stuff like the contact rate and the modifying parameters that are introduced. So also the idea to try and analyze these ones, like the contact rate and the modifying parameter, is because they play a major role when it comes to the force of infection. So let me just try to zoom in. So the first one here is for the first wave, and this will be for the second wave. And then now, the red one here, as you can see that if we try to increase the contact rate, let me see. Just give me the moment. If we try to increase the contact rate, which is psi, you will see that on the red one, Oh, what's happening now? Yeah, on the red one here, you see that the peak, it becomes very high. That is when we increase the contact rate. But when we decrease it, you will see that the peak of the green line, it becomes a little bit lesser. Similar applies to the second wave. And then the blue one is the standard one of the fitted that we had from above. And then now also, when you do the very same thing for zeta, you will see that if you increase zeta, meaning that now most of the people in the exposed compartment, they are able to spread the disease. You will see that we have a higher peak for both waves, and then if we decrease it, we have a lower peak for both waves. And then now this was the interest. Oh, this now is for the transmission rate. So you see that if the transmission rate is higher, it behaves likewise as we explained earlier. And then now this is the quarantine rate. This is the quarantine rate now. So you see that if we have less quarantine, you see that the peak is higher, even in both ways. But if we have higher quarantine with the green graph, you will see that it is a bit lower. So the conclusion was that alpha is directly proportional to R0. So now with that, we're able to tell that if we are to decrease the force of infection, which depends on psi and zeta, we're able to decrease the R0. That means that the prevalence of the disease will go lower. And then also, we're able to see with the R0 that isolating infected individual is good, but it must be administered at a higher rate. And also, it would be a bit expensive because of infrastructure for other countries that doesn't have infrastructure, or even for if we have a higher population, we might run out of infrastructures to put those people there for isolation. And then also, with quarantine alone, we cannot quarantine like almost everyone. So it would be best to control mobility by just taking everyone to lockdown at the early stages of the pandemic, which is what most countries did, like countries like China at the time. So these were the references. Now, for future work. So the idea now is that we want to try by all means to have to increase the accuracy of the model, because some models are having like a lot of shortcomings and all of that. So we are going to try and implement what is called the optimization, which is what is this? It's called it's a feedback feedback mechanism, something like that, to try and increase the accuracy of the model so that we are able to tell at what time and at what rate should we, at exactly what time and at what rate should we exactly implement things like the vaccine and all the other strategies to try and mitigate the spread. So that is the future work. And also, we are now interested in involving something called the standard finite difference schemes for optimal control. So that is one thing that I'm going to be looking at next. And also we have some, for this study, as I mentioned, that there is a study that I'm doing, which is an expansion of this one because of the shortcomings that I saw. For example, vaccine and the indirect transmission, having and including the environment in the model also. So that is one thing that I'm working on now, which maybe if God allows, I will present it in future. But it's almost done. And also I have some work on sclerosis, where I'm looking at vector disease. So there we just have two populations, which is the vector and the human population, but they interact. So yeah, that is the work that I'm doing now, which all came from this idea, because this was mostly like my first work in mathematical biology. So yeah, that is what I'm doing now. I hope I didn't take much time. Thank you.
Thank you very much. We would like to ask you some questions now. I hope you're available for that.
Yes, I'm available, sir.
Thank you. By the way, do you have a camera? Would you like to switch it on?
Yeah. Let me just switch on the lights first. Let me stop sharing and then camera, use camera. Oh, I have this thing on. Can you see me, sir?
Yes, hello, nice to see you.
Yes, thank you. Nice to see you too.
Are there any questions? From, I do have a question, but maybe first there are some questions from the floor.
Yes.
Anyone? Remarks, comments, questions?
Good morning, Mr. Makagula. Thank you for thank you for the nice presentation. I'm not sure if I captured you correctly or maybe I missed something. I just want to understand the kind of modeling. You said you're in modeling, so I just want to understand the kind of model that you used and how does it work in comparison to other models. Thank you.
Let's say I used a compartment because, as I mentioned, that this was like my first work on the field. So this I used a compartmental model. What I know is that I'm not really sure what other models we have, but I know that we have other models like there is. Here I was using OTEs. There are other models that uses PDEs. I've solved some they include stochastic and all of that. But this one is I think it's the entry one, where that once you understand these ones, you can now diverge to the other ones. Yeah, so here I was using OTEs.
Thank you. You have a question?
My name is Akele. So your model can be extended to like other or like is it strictly working only on like epidemiology, or it can be extended maybe to like financial markets and other things?
I think it's only on epidemiology because remember when we do modeling, there is no way that we can model without understanding the biology of the disease itself. So I think for you to take it to that side, it must be something. There must be some similarities in a way that if I'm in finance, I don't think there are any. Maybe there might be an idea to take it to that side, but at the moment, I don't think so because of here I was looking at the biology of COVID-19, for example. You see, so I don't think it's possible to, but there are models for finance, as we know, which I don't think that they are related. Maybe the use of OTEs is there, not maybe, it is there, but then look, taking this model exactly the way it is and trying to take it to finance, I don't think so.
I think it's you.
I would also like to ask you a question. Could you please go back to your slides and specifically if you could open the slide where you had a diagram with arrows?
All right, share window. Now, can you see it now?
Yes, the slides are there.
Yeah.
Yes, that slide. So
Yeah.
in this diagram, is there any meaning to consider, let's say we are at S, right? And we consider going from S to I. by first following alpha and then following beta. So basically, the paths
So
we can
jumping
following
jumping
the
E. Jumping
not,
E.
not jumping, no, but going via E. Is there any meaning to the potential arrow from S to I that would be obtained by combining that first alpha then beta?
All right. Let me put it this way. So all of this, also any model that any method like epidemiological model that you're gonna see is an expansion of the Mark-Henrik and Lamarck model, which is called the SIR model. So the first model that we had was not having an E. It was only S, I, and R only. So there is a case like that, but
No.
when you
That's
become
not what I'm asking. That's not what I'm asking. So what I'm asking is, if we travel in this diagram by following arrows, let's say, for example, we go from S to E, from E to I, from I to R, and then back from R to S.
back from, yes, there is, here it is. Yeah.
So this loop going from S to back to S via E, I, R, does this loop have any significance in what you're studying?
Yes,
What
it
does it
does. So
represent?
the idea is that, you see, let me just talk about COVID. So there are some diseases after recovering, you don't have permanent immunity. You will have temporal immunity, but after that, you're gonna come back and be susceptible again. So you can get the disease again. So the idea now is that after recovering, you go back and be susceptible. That is what that arrow is capturing.
Okay, so you're saying that combining these arrows does have some meaning, right?
Yes, so the arrows, you see, the arrows, they show us that these individuals, you see, for example, from S and E, they move to E. From E, you move to I. From I, you move to R, or you move to Q, or you die. So they do have meaning. Basically, because I didn't have time, I didn't explain this. So this is what is happening. These arrows, they are the ones who are able to tell us the rate of change of each compartment, because as you can see here, I'm having some negatives here, I'm having some positives here. For example, let's click on both of this one that you're talking about. Here I have a positive WR, right? And omega R. And then here, if you check, I have a negative omega R. Why is that? See that it's positive on S, it's negative on R. So as you can see here, this arrow here, the reason why it is negative on R is because on R is going out, but coming in on S. So if it's coming in with this arrow here, you will see that it's going to be positive here. But if it's going out, it is negative. So that is the meaning of the arrows.
Okay, here's another question. So if you go from I to D directly, right?
If you go from I to D.
I to D directly via N. Is it N there? No, sorry. I think it's eta.
It's eta. That's a parameter.
Yeah. And then if you go to D via Q, so if you first follow epsilon, then tau.
Yes.
Are there sometimes cases where these two processes overlap, or there is some kind of relationship between them, or are they completely different from each other?
Please repeat again.
So the path from I to D that follows eta,
yes,
the one that that goes via Q,
yes,
are they completely independent of each other, or can there be some kind of overlap between them?
Nah, they are independent, because the idea here is that remember that if you're in quarantine, you are well taken care of, right? So, and then now if we are in I, you are just there outside by yourself. So the death rate won't be the same. So that eta and that, they represent the disease-induced death rate. from Q and from E. So they are just independent of each other.
In the same way, the arrow going from I to R is independent from the arrow going from I to Q and then Q to R.
Yes, they are independent.
And in these diagrams, is it always the case that two paths along different sequences arrows will always be independent, or there are some cases when they might not be completely independent?
I think they are independent because this is for example, the compartments themselves, they are disjoint, so they have to be independent.
So in such diagrams, they're always independent.
I think so. I think so.
Okay.
Yeah.
Thank you very much. The reason why I'm asking you this is because of mathematical structure called a category, which looks very similar. As a picture, it looks similar to what you have. But in a category, we have such pictures, but then what we do is we follow arrows in a path, like I was trying to suggest. And then sometimes we have two paths that, even though they go via different route, they still end in the same result. So they're not always completely independent. They can be independent as well. With my questions, I was trying to understand better what link could there be with these models that you create from the diagrams and with the structure of a category. But we will deliberate these things more today, I hope. That's
Yeah.
from my side. Thank you very much for the presentation.
All right, thank you very much.
And any other questions? Okay, yeah, thank you again.
Thank you very much, sir. And thank you for the opportunity for me to present what I'm doing and what I'm able to do.
Sure, thank you. It was very interesting to listen to you. Thank you very much.
Thank you.
Okay.
Prof, my question is it your wish to find everyone here which focus area they are interested in, and then find them maybe a supervisor or a mentor to work under, or it's your wish for everyone here to be under specifically your focus area, which is mathematical structures?
Yeah, so the plan is for us to consider possibilities of everybody joining the focus area of mathematical structures, which is one of the focus areas at NITEX. The reason for that is because this workshop is funded by the focus area. The other focus areas didn't contribute or even, as you see, participated in the workshop. But of course, if after the workshop you're really interested in some other focus areas at NITEX, definitely we can find somebody that you can contact. But our time that we spend here, maybe could you open it, please? Our time that we spend here, we should try our best to see how we can incorporate everybody in the focus area. But that doesn't mean changing your direction of study. It means integrating your direction of study with focus of the focus area.
Okay, Prof. I would say rather what caught my eye outside of everything would be the incorporation of category into Lee, and also the one of ideals. So that's what has caught my interest.
And then what did you say about ideals?
So also how it would fit into
List symmetry theory. Thank you. What else should we put on the board?
Okay, I would say more of a comment. Looking at the structure, what was explained yesterday in terms of category theory, right? As much as maybe graphs would be falling into a different focus area, but I feel like
sorry, to interrupt, just to fix the terminology. The term focus area means something very specific. It means one of the 10 focus areas of NITEX under which we all are now. So this is the focus area of mathematical structures. It includes graphs, it includes categories, it includes ideals, it includes many other structures. So graphs is not a separate focus area.
Okay. Yes, and that's why the next statement I was going to say, but I feel like it goes a bit hand in hand with category theory, because as what's her name? Yes, as she was explaining there, I could see some graph theory from what she was working on there. So I think that relationship between category theory and graph, it's a bit interesting. And in the beginning, I thought of they were separate. There was no connection or intersection between the two. But as she was explaining category theory, I could see some graph happening there. So that's the most interesting part I got from it.
Fantastic. So relation between graphs and categories.
Any others?
I think maybe we can engage on this as we are engaging. Maybe they will have some ideas of what else to
Yeah, we'll definitely start engaging on these things. So at the moment, we just want to put all the ingredients for engagement, including some suggestions. I think you have also something that you've prepared that you want to propose, right? So we can also put all of this. And then so this session is just to do the roots. Then we will start engaging. Of course, as we start engaging, there will be more ideas that come.
And maybe the last thing, how ideals fit in every form of mathematics. Because when you're explaining ideals there, you were actually sort of touching to how it connects to every aspect of mathematics. So that's also kind of interesting.
You might notice that as we're putting things on the board, when you say category theory, I write categories. When you say graph theory, I write graphs. So I'm making emphasis on the structures rather than on the disciplines. The idea there is that each of these disciplines are shaped by not only the kind of structure they study, but also the kind of problems they look at. And so then it gives some kind of feeling of what the boundaries of the discipline are. But now when this happens across decades, right, these disciplines start evolving separately from each other, and then they become their own independent silos. And so what we're trying to do now in this focus area is to break down those walls. So that's why we're focusing on structures rather than the disciplines. We want pandisciplinary approach to mathematical structures, which is something that you already do. Like, for example, what you do is already pandisciplinary because you look at graphs in chemistry. So it's already there. But we want more, like, for example, linking categories and graphs. Another. Any other ideas what we could incorporate today? Anything from you, Dr. Abass?
Maybe for now, no, but then before the end of the year.
Sorry?
For now, let me say no, but before the end of the year, I should be able to bring goals.
Okay.
Maybe what we can also try is the aspect of algebra and matrix structures. If it's going to be possible. Yeah, matrix structures with algebra.
The problem what I thought is exactly.
Metric structures.
That's what you thought.
Yes.
Yeah, matrix structures and yeah, algebra structures.
Metric structures versus algebraic structures. Yeah, this is a very interesting topic.
In fact, last night I came up with an idea. Of course, it need to be checked whether it will work or not because I didn't do research, and it is about how to do some kind of metric theory study with some very, very concrete algebraic structures. Let's see how much they will like it. Anything, please feel free. We don't promise every wish will be fulfilled, like in real life, but no harm to express all your wishes. Wish list. This is wish list. Yes.
So I think also we can also incorporate this instead of matrix, we will use the normed spaces to yes even yes. into
Sorry,
algebraic
can you say it again, please?
Along with the metric spaces, also norm spaces. Attaching the categories.
Yes.
So what Professor Aphane says, the connection between metric structures and algebraic.
I think norm. I would understand metric structures very broadly here. That probably includes also normed, but we can maybe add it explicitly. Yeah.
I mean, from norm you get metric, right?
Yes, yes.
Metric and normed structures versus algebraic structures, or are we going to be changing what you had in mind?
No, we don't check.
Yeah.
Yeah, whatever that will come out. Maybe the other thing is the basic structure with a graph structure.
Linking metric and graphs.
So maybe you put comma, metric, norm, graph.
Yes.
No. That sounds something separate. That's metric and graph coming together. This one is metric and algebraic structures coming together.
Yeah, then he also wants norm and algebraic structure together.
Yeah, but norm and metric are
Also related with each other.
related. Yeah, so I'm gonna put norm here.
Yeah.
But the other one I'm going to make it separate. And in fact, I'm going to put this as well because it turns out that the metric space is actually a special kind of a enriched category. There is actually a link there as well. So that could be a way to link the graphs as well.
Something in the chat.
Yes, Kishan.
Good morning.
Something in the chat.
Oh, someone is on chat. Zurab.
Hello.
Good morning. Can I interfere just from online? I had put a chat saying mathematical structures, how they link in layers to mathematical disciplines. I don't know whether that makes sense.
Could you maybe say a bit more what you have in mind?
In mathematical structures, how do they link with the mathematical mathematical disciplines, maybe in terms of layers? I'm thinking of from the community side, how one can introduce mathematics in terms of the structures and then how they relate with the disciplines.
I like that. So how can one introduce mathematical structures to the community?
Yes, and then how they relate with their disciplines now coming separately, but first with the structures, then drilling down to the disciplines.
How the structures are related to disciplines.
Yes. Thank you.
Thank you. Thank you very much. Yeah, this is actually one of the, I'm really passionate about this topic. And a lot of times in the Future Mathematicians program, we try to address this question. So thank you, Johnny, for that. This is not quite, well, it can be a research topic as well. You want to explore how to convey understanding of mathematical, like for example, groups, symmetry, right? You can explain what a group is by explaining symmetry, and then that links with symmetry as well. So it's an interesting topic. Any other suggestions?
I was thinking of introducing a complex spaces linking with the algebra. I'm not sure. That was
Linking with
my
algebra. Did you say algebra or?
Yeah, we can link it with algebra, but we introduce the complex spaces.
By complex, you mean complex, where scholars are complex numbers?
Yes.
Yes, that's possible. Very much possible.
So there is some kind of a broader theme that I can observe emerging here, which is if you look at if we think of lysometry as some kind of geometry, because really that's what it is, right? Differential equations kind of describe the geometry of how things work. There is geometry here. There's geometry there, graphs of geometric structures. There is geometry here, metric and normed. There is geometry here and here as well. And then there is geometry here. On the other hand, we can think of categories as algebraic structures. You can see that many of these themes are about linking geometric and algebraic structures with each other more broadly. And in fact, in the focus area, there is a project that I lead, which is unifying geometry, how's it? Algebra, topology, and logic. So it nicely falls under that topic. Any other suggestions, what we could add to the list?
Okay, so I was thinking of how can we incorporate graphs with maybe linear algebra, or maybe if not linear algebra, it could be applied in terms of applied mathematics, in terms of maybe optimization, something like that. Because with the presentation, you could tell whatever Zakele was doing, you could tell there was sort of graphs there, graphs. So because I'm more into applied things, so maybe we could incorporate graphs with applied in terms of maybe optimization. Or yeah, that's what I'm thinking.
How graphs at the organization fits into
Well, graphs themselves are mathematical structures. And I think the question is, what are applications of graphs in optimization, right?
Yes.
So I think it's a nice question. I know almost nothing about this, but now tempted to open Google, Google search and find something.
There is one concrete applications of graph in optimization where they use for the traffic problems. And Professor Simon Mukwembe is one of the persons who actually worked on these optimizations using the graphs. The other one was he also worked on using graphs in another kind of optimization is to minimize corruption in a country. And his model was actually Zimbabwe. But there are, of course, many other optimizations here. So different invariants and minimal graphs. So those kind of notions they are actually using for this optimization because you wanted to minimize something in a vague sense. And then you wanted to use this graph theoretic properties invariants to model them. Very similar what Fatlane is doing, that he is using this graph theoretic invariants for the molecules or certain kind of chemical compounds. So the approach is same, but of course, your mechanism will be different because your applicability areas are different.
I would like to add something as well that was something in the back of my mind, but then it resurfaced after this morning's presentation. Categories in mathematical modeling. Specifically, this question I was asking about the diagram that was shown, that was used and write down the differential equations. It kind of links maybe slightly with graphs and optimization because in other cases, it's arrows and vertices. I'm gonna put this next to the other one.
I think we have quite enough Zurab now.
No, we're not going to necessarily do all of them.
Yeah, of course not.
Just
Yeah,
give freedom everybody to
sure.
suggest
Okay.
ideas.
Okay.
So say again.
Optimization.
No, but rather the other way around, because so optimization is a specific type of a problem. Yes. And we want to focus on structures. So we can ask how norm structures can be applied in optimization, for instance. But I wouldn't want to put optimization on the first place because it's a problem. Yeah.
Maybe you can make a slash graph slash matrix structures in optimization, something like that.
But is this not something that you already do? Any other ideas? But Professor Goswami, you had something that you wanted to propose, right?
That already covered by Aphane and someone said about this.
You don't have a more specific formulation.
I have absolutely the three formulation, but
Let's write this down, questions here, then we can link to the.
Okay. So, leading matrix based theory on settings. It's really something by Professor.
So you're saying that this links with metric and norm structures versus algebraic structures. What was the other one?
Other one is about realizing that something of ideals in settings, which are intervals for rings, not really for settings. And it's got strongly irreducible ideals on settings.
So which one does it?
How ideal fits across mathematical structures.
Well, isn't it a bit too narrow, because ideals are already from rings and semi-rings are very close to rings. You're not really going across, being quite close to rings.
Can't actually work on ideas in all structures together. That will not make sense. Because the definition of ideals will change according to the definition of the structure.
Well, maybe, so you already have on semi-ring, so maybe doing metric space theory and semi-rings maybe could involve also ideals on semi.
Yeah.
Anything else we want to add to this list? Well, we'll be choosing some of these
Yes.
to focus on.
Thank you, Aphane.
Okay, so then maybe now we can start trimming down list a little bit to make a choice of some of these topics. We are still in this session, and so we have 15 minutes left, and in these 15 minutes, maybe we can highlight some of these topics. Then in the next session, this session, we're going to add all the mathematical ingredients we will need for later discussions on the board.
Actually work on the board.
Yeah.
But we like to focus on a problem so that it will be related what you were going to present after that.
Yeah, we should identify now research questions. Yeah. So to start? Yeah, we have to formulate research questions now. That's also what I was. So what would we, so we want to make some concrete research questions out of the broad topics that we identified. So maybe we can begin with yours because you already thought about it. So when you say doing metric space theory and semi-rings, what is the specific research question that you think could guide us?
Also, metric on a semi-ring instead of a set. Define metric on set. So now we define a metric on semi-ring. So instead of x cross x, now we have semi-ring cross semi-ring, product of semi-ring, and then here.
Wow.
And then we have to add some additional actions apart from metric space action, so that this addition and multiplications also came there.
And then the notion will be called.
I call it invariant metric because there is some kind of invariance on that metric property. But of course, this I just thought last night. If it were, and my guess is that that metric on semi-ring will make a semi-ring actually a topological semi-ring. So your addition and multiplication will become continuous using that metric. And then you can define norm on it. Then you can do whole fixed point theory on semi-rings.
New definition has come in. Did you hear him?
It's all I thought. I mean, how much it will work, I don't know. I mean, we have to work it on because I didn't do research. I just came up here last night.
You take a metric space, you take a metric.
No, I get a semi-ring.
Yeah, no, I was gonna come to that part.
Yeah.
So instead of a metric, and then you now put in a semi. And then you put in the properties.
Some more.
Yes. Wow. And then you can define whatever on the new structure. Okay. You can write it down. I think that is the first thing.
Okay, so we've got one research question I can see. You're right on time. We are identifying research questions for.
Okay, that's perfect.
But which of these topics are the ones that are very, very interesting? Let's prioritize some of them. If we can guide us what question to identify. Let's vote. For each of these topics, I'll ask you to raise your hand if you think this is like super, super interesting for you. And then we can see how many votes which one gets. The first one, raise your hand, please. One vote. 2 votes for the first one. Okay. Introduction of categories and ideals, incorporation of categories and ideals into split symmetry theory. How many hands do we have for that? 2. 1. 1 hand in the back.
I also vote for that. I don't know if I've...
So 3 hands.
I also want to vote, but I don't know if I get a vote.
You can vote, yeah.
Can his vote be counted?
Yes. Keep your hands up. So please, we have to do it quickly. So 4 hands. Okay, 4 votes for this topic. Relation between graphs and categories. 1, 2, 3, 4, 5, 6, 7. How ideals fit across mathematical structure. Okay, we've already covered, I think, ideal part. Metric norm structures versus algebraic structures. We already have research questions for that. Metric structures versus graphs and categories. How many hands for that one? Metric structures versus graphs and categories. Maybe it goes close to 7, yeah. How one can introduce mathematical structures to the community and how they relate to disciplines. Raise your hand if it is super interesting. How can one introduce mathematical structures to the community and how they relate to disciplines? Raise your hand if it's super interesting for you for today's discussion.
So I think also it can help in terms of community engagement.
So you raise 1 hand.
There's a research question.
Yeah. There's 1 hand. I'm not casting my votes at this point. Complex spaces versus algebraic structures. Raise your hand. 1. Graphs and metric structures in optimization. Raise your hand. 1, 2, 3. 3 hands. Sorry, 3. Categories in mathematical modeling. Raise your hand. 1, 2. 2 hands. 3. Okay. I think the winners are the first 2, right? So we have, we now need to formulate the research question on each of these. So we have research question 1 that came from Professor Goswami that was linking with this topic that we identified earlier, and also linking with this topic. These 2 topics are covered in research question 1. And now we voted for the interest, and so we have. No, we didn't vote for these because we already had a research question for that. No, there was a lot of discussion, so I think that, yes.
The second last
Graphs and metric structures and optimization.
And when you go to number 1, 2, 3, 4, number 5 from the top. So number 5 from the top, we have metric structures versus graphs.
Yeah.
And categories.
Yeah.
And then we have graphs / metric structures in optimization.
Yeah.
I'm thinking the 2, can't the 2 be combined? Then we have metric structures versus graphs, then in optimization.
Well, nothing excludes us from looking into optimization or any other disciplines in any of these topics. So I think this is more about the structure side of things. Although this symmetry theory is again a discipline. I think optimization can be brought in any of these. So let's identify a research question on each of these. So these are the two that is most interest. This one and this one. Let's begin with this one because this had most votes. Relation between graphs and categories. What would be a research question there? What about the following? I propose one, but if you change it, it's fine, we can change. Are there hidden categories behind graphs as studied in graph theory or its applications? Because a graph is a data of vertices and edges, right? Directed graph is directed edges. Now, is there actually a category going on there which maybe is not explicit, but it may be implicit and irrelevant? Like the kind of question I was asking earlier about the graph we had, the diagram we had for the modeling. Is there a hidden category there? You think is a good question? Okay, great. So we have.
This includes trying to construct a category associated to a molecule.
Yeah, yeah, it includes that. Yeah. So we have research question 2. Since we already have categories featuring in this research question, I would suggest that we drop the first one. Also because we will need Abdul Kara for the first one, and he's not going to be here today. Unfortunately, he's at the University of Cape Town. Yeah, and Ali is also with him. And without Abdul Kara, I think we will. Yeah, I don't know structural aspects of this that well. We can, we can park it. Yeah.
We should keep it in mind.
Of course.
As soon as after.
Absolutely. In fact, I'm going to delete now the voting numbers here.
After this is not the end of this.
Of course. I'm going to delete these numbers so that we can all. So it doesn't feel like some of them are more important than the others. I'm just saying that in terms of identifying research questions, we already have 2 questions. And the question is whether we want a third one or not. So we have categories are here, graphs are here, metric structures are here, semi-rings are here, rings are here in this form of semi-rings. Are there any other mathematical? Let's look at our map. We had a map of structures, right? Let's look at our map that we really included. Lie algebra, Lie story we're not representing here, unfortunately, right?
So Lie part can be represented with Lie algebra.
Yeah.
I don't know how even ideals can come.
But you probably don't know what a Lie algebra is, right? You only know this Lie symmetry method in the. So we don't have expertise today to that. So what else?
Probability is
So this is our map.
When we start with the
So Hilbert space is
actually on the research question 1.
I have no idea whether it will make sense or
we all
just an idea.
So we'll see how it plays.
spaces. Yeah. Right. So you're saying we have research question 1 linking metric with semi-rings. We have research question 1 linking categories with graphs. You seem to be proposing something that links something from question 2 to
spaces and the
but it feels to me that people who are interested in metric spaces, they will be working on research question 1. And we don't have so many of them anyway, so
okay.
Anyway,
Maybe at a later stage.
We should fulfill it.
We should be yes.
Yeah, because we're still going to have more projects. Other issues are just.
Yeah, this is just to do some kind of practice here. I mean,
Let's
this is
start
a
with
starting
this
point.
one.
Yeah.
Let's start with this one so that they see.
You get some idea, you warm up, you suffer, and you enjoy, and then eventually your master's project will be able, but you will give an idea how structures works, how structure interacts. So this is just a practice, something.
Yeah.
So finance can be brought in under research question 2, because we're talking about the applications, and so optimization and finance can be brought in under question 2. I think the optimization and due to link to Hilbert space can also be brought under research question 1 under metric space. So I think we can all try to bring in our inputs and agents. Great. So we are at the end of the session. Now it's Roybo's break, and we've managed to do what we wanted to do, to identify research questions. So we will then let me just remind you that from 11:30 to 12:30, we will be unpacking a bit of mathematical structural things. Like, for example, maybe we should revisit the definition of a category, or we should look at the definition of a semi-ring, all the mathematical background we need before we start engaging with the research questions. That will happen from 11:30 to 12:30. And then we'll have lunch, and then after that, we'll start actual work. We're going to split into 2 groups, yeah. Maybe we would want to also split each group into so that everybody can talk to each other. Because if there's one big group, the danger is that one or 2 people will be talking and the others will be silent. So we might split into 2 groups, but then each group might also split into subgroups too. And I think each group can decide how they can work.
Yeah. Still, maybe it's just have.
Okay, great. We'll resume in half an hour. All right, welcome back, everyone. So,
it's what you see.
in this session, we'll look at structural insights into the research questions. We will begin with some background for research question 2, and then we'll move to some background for research question 1. There is something I want to say for research question 2. I'll take a few moments to say that, and then I'll hand over to Elena, Luca, and Kishan, and also from the graph theory side, if there's anything we need to add, especially for the students to have in mind. And then I, unfortunately, will disappear. I have lecture to give from 12 to 1. And then I'll join you again. But Amartya will take over for giving some background on research question 1, especially what a semi-ring is. We'll take it from there. If we can begin. Yeah. So the research question 2 is about trying to find student categories behind graphs, studying graph theory and also applications of graph theory. I was giving a course at Ames on category theory, and I decided to think of ways where the concept of a category can be explained in most intuitive form to someone who hasn't seen categories before. And then I realized that this line of thought could potentially open up a lot of new applications of category theory, which one might not have thought of before. I still haven't had a chance to experiment this, but hopefully we will have a chance to experiment this today. So if we begin with a directed graph, how to arrive to a category, that's what I'm going to show you now. That hopefully will help us with research question 2. Let me begin with a very strange kind of directed graph, something that's not a typical example, maybe. I'm going to take the set X having 3 elements, 1, 2, and 3. And I'm going to build a directed graph of subsets of X. I'll begin with the empty set. Then I'll put all the 1-element sets. And then I'll put 2-element sets. 1, 2, 2, 3, 1, 3 rather, and 2, 3 here. And then I'll put the unique 3-element set. And then I'll draw the edges. These will be directed edges. They will always be directed upwards. And the edges here indicate that one set is a subset of the other. And you can decide if you agree with me or not with my drawing of the edges, if maybe there is something that shouldn't be there. Already this one shouldn't be there because this set is not a subset of that. Probably some of you know that we are supposed to get a cube, right? We actually get a cube, the picture, but it doesn't look like a cube because I made a mistake. This way. If I had a 4-element set, we would get a 4-dimensional cube, which is a nice thing to draw. So the presence of this edge tells me that one set is a subset of the other, but it doesn't describe all the subset relationships. For example, this is still a subset of that, but we don't see an arrow going from here to there. There's no arrow. But instead, what we do see is a path of arrows. And we don't draw this arrow because we know that we can get it by taking path of arrows. That's what a category is. When you have a directed graph and you start considering paths of arrows, that is what a category is. In this case, if I start at one vertex and I want to go to another one, there are possibly more than one ways to do that. Here I could take this path, or there I could take this path. The two different ways of getting there do not give me any additional information than this is a subset of that. So we can say that this path is equivalent to that path. But in the example we had in the biological model, remember I asked the question whether two paths were the same, and he said no, they're actually disjoint, nothing to do with each other. So we can get examples where two paths are not necessarily equivalent to each other. They're not equivalent to each other. And then we can get a mixed situation where sometimes two paths are equivalent and sometimes they're not. So if I take a directed graph and I put the information of when are paths equivalent and when they're not, then I get something that would be a category. It should satisfy some axioms, but the axioms are very natural axioms to be satisfied. So intuitively, that's really what a category is. It's a directed graph with an information of when are certain paths giving me the same result as certain other paths from the same vertex to the same vertex. And my conjecture is that this way of viewing categories should help us discover many interesting examples and applications, hopefully also, of categories in other areas. Because in real life, we don't really see infinite things. We only see finite things. But you can make infinite things out of the finite things. Take, for example, the set of natural numbers. And take the function that maps every number to its successor, to the next number. The +1 function. We can draw this as an arrow. So this is a function that takes an input and adds 1 to it. So let me just draw a star here. The star is a placeholder for an input. This is also a directed graph. In this case, we only have one directed edge, right? But now I could take a path made out of these arrows. I could take this arrow and then combine it with itself, and then combine it again with itself. So if I started with a function f of x equals x plus 1, if I do it twice, I compose the functions, right? This will be f of x, which will be f of x plus 1, which will be x plus 1 plus 1, which will be x plus 2. So we get a different function to the one we started with. So this arrow taken twice gives it a different object. 3 times it will be +3. 4 times it will be +4. And so we will get infinitely many of them, right? Because we will get as many as there are numbers. But we started with a finite thing, which started with just one operation. So in real world, we never see infinite things. They're always finite. But when we start following, so directed graphs coming from real world are always finite. But when we start following paths of arrows in a directed graph, we can then get infinite objects as well, like here. So this would be a category, an infinite category, just like this one would be a category. The difference between these two categories is that in this category, you kind of have very few arrows. Like, for example, from this vertex to that one, you can only have at most one arrow, because the existence of the arrow just tells you that one thing is a subset of the other. It's a relationship. It either is a subset or it isn't. So either there is an arrow or there isn't. So here we get what is called a partially ordered set. What is a partially ordered set? It is a set X equipped with a relationship. In this case, it's a relationship of subsets. And the set in question here is the power set of X. You're familiar with the power set of X? I'm asking the students. Yeah. So the power set of X with this relation. This relation of subset, which is obtained by following the paths, has two rules that it satisfies. A is always a subset of A. And if A is a subset of B and B is a subset of C, then A is a subset of C. This is what enabled us to do that, right? To do one subset relation and another and get a third one. So a partially ordered set is actually a special kind of a category. It's the kind where if there is an arrow between two objects in a given direction, there is only one arrow. There can't be more than one arrow. Whereas here, it's kind of the opposite. There are lots of arrows, in fact, infinitely many, from the same object to itself, but there's only one object. So here we have maybe many objects, very few arrows. Here we have many arrows, one object. And this special kind of category, when there is only one object, is called a monoid. So what is a monoid? A monoid I'm going to divide this in two parts. A monoid is a set. In this case, this would be the set of functions of this form, right? So it's the set of functions of the form star plus n, where n can be any natural number, right? So I'm just using this notation to represent one function like that. And then what we can do is combine them. We can compose them. We have an operation of composition. And what are the axioms? Well, one of the axioms is that I have this special function called the identity function, which is star plus 0. You might think, how can we get star plus 0 out of this? No matter how much we combine, we get higher and higher number. But I could say that let's combine this 0 many times. And let's agree that to be star plus 0. It's just an agreement. So the identity function, which has the property that if I compose identity function with the any other function on either side, I get back that other function. So the function of adding 0 will not change anything, right? And then the second axiom is that we have associativity. So F composed with G composed with H equals F composed with G composed with H. And these are familiar axioms to some of you, because if I add one more of existence of inverses, I get the definition of a group. Oh, we have. Okay, fantastic. Yeah, so that's exactly the monoids that Professor Goswami talked about. So a monoid, which is a generalization of a group, is actually a special kind of a category. It's a category where there's only one object. Whereas a partially ordered set is a special kind of a category where there are maybe many objects, but between any two objects in a given direction, there is always at most one morphism. In fact, there is another condition that needs to be satisfied, which is called antisymmetry, but I'm skipping that part now. It's actually more correctly called a pre-ordered set rather than partially ordered set, but this is now technical differences, which doesn't really matter for today. So between these two scenarios, where there's always at most one morphism in a given direction, and when there is always one object, there could be intermediate scenarios where there are many objects and many arrows as well in a given direction. And when people say they do category theory, it's really studying the intermediate ones. Otherwise, if you just study these, then you're doing order theory. And if you just study these, then you're doing abstract algebra. Okay, so that's all I wanted to say. I just wanted to explain that to get a category from a directed graph, you take your directed graph, and then you ask the question, is there any meaning in composing the arrows, in going along paths of edges? Is there any meaning in that? And if there is a meaning in that, is there any meaning in declaring that sometimes two different paths can give rise to the same outcome? If there is any meaning in these two things, that means that we are then going to be working in a category. If not, then the category isn't there. Okay? Yes.
That's why you were asking him if there's any meaning in his graphs. So does it mean the whole
I think it does mean that, because when there was a loop, remember when there was a loop, that loop was different from doing nothing. So even though in the other cases the things were disjoint, which means they were of this kind. No, they were not of this kind, sorry. Sorry, let me revise the answer. He said that if you have like a situation like this, for example, there was one triangle like that, right? He was saying that this path is not the same as this one. That's actually good news, because it means that in this category, we have two morphisms in this direction. One is the blue one, and the other one, red one, is the one that goes via that one. So we actually don't have the situation. Neither we have the situation. We really have a situation where in a given direction, there can be more than one morphism. And there was another diagram where there was a kind of a loop going back, and that now gives this type of thing, and now you can iterate these a few times. So there was definitely possibly there was definitely a category in what he was doing. That's for sure. Of course, the next step now is to see if studying this category can be useful to the application that he had in mind. Any other questions for me? If not, then I'd like to ask others who would like to contribute to some structural insights for research question 2. Anybody would like to add anything more? We still have 12 minutes for that. And graph theories.
I think you covered because a directed graph is more of moving from one vertex to the other, but with direction, right? So as we can see from the subset 2, that you were able to create 2 parts from there to the main set, which would be via 2-3, subset 2-3, and subset 1-2. So subset 2 is connected to main set 1-3 through the path of 1-2 and 2-3. So that gives direction. In a general or a simple graph or undirected graph, we could say we could move from 1-3 to 2. But in this case, we can't, because now the direction is going up from 2 to 1-3. So I think everything.
Maybe I'll just make a quick comment how we can also capture undirected graphs as categories. We can. So imagine we take a very simple undirected graph. Let's say a graph with 2 objects and with 1 edge. This was one of the main examples in the other day, right? So what we can do is to say that first of all, we need these identity things, an arrow from an object to itself that doesn't change other morphisms when we compose with them. It doesn't change other arrows when we compose with them. So we'll have to add these loops here. Okay, but then we also need something to represent this, and we can only do it by direction. But then what we can agree on is that every time I have a direction going that way, I also have a direction going backwards. And then I can agree on that this composed with that is equal to the identity. And also on the other side, this composed with that is equal to the identity. This kind of a category is called a groupoid. This is called a groupoid because if there was only one object, imagine a situation like this where instead of natural numbers, we have integers. Adding 1 has inverse subtracting 1. Adding 5 has inverse subtracting 5. So this is when our monoid would become a group. So a group is a one object category where every arrow has an inverse. But now if I have many objects where every arrow has an inverse, then it's called a groupoid. So it's a bit like defining an undirected graph by a symmetric relation. Relation is symmetric, means both, if one is related, then the other way. Yeah? So any undirected graph can be also viewed as a groupoid. But maybe in an undirected graph, like the one that comes from a molecule or some other situations, if you follow an edge and you go back, maybe you don't want that to mean nothing. Maybe you still want that to mean something. So then this would be not a groupoid anymore. Coming back is not quite the inverse. And the fact that you went there and came back now represents some information that you're able to capture using a new looped arrow here. An interesting example of this would be human interaction. Let's say, what's your initial? Remind me, please.
Yeah, MG.
Can I put M? So Zurab and Z and M are talking to each other. So this undirected graph represents our conversation. I'm telling you something, you're telling me something as well. But now our exchange of information creates some thoughts in me, right? And that process of creating thoughts can be represented by, so we are talking, I've now turned the directed graph, so the undirected graph, into a category. But the fact that we're talking, this path is no longer doing nothing. It would be very different if I was just on my own, blanked out, no thoughts going in my mind, right? That would be the example of the identity more. But here, when we're engaging, this back and forth actually creates some thought process in me. And this thought process could be represented by a new arrow here, which is not the same as the identity one. So this would be another way to turn an undirected graph into, now this time, really a category, not quite a groupoid. Elena and Luca, would you like to add something, or Kishan?
I have an idea, but maybe it relates more to the last categories in mathematical modeling.
Mm-hmm.
So I don't know if this makes sense completely, but from what I saw, I think the talk in the morning, there was a directed graph, and I think those edges, they had like weights to them. The edges had weights to them. So it was some type of directed graph where the edges have weights. Now, for any graph, we can form a category from that graph. For any directed graph, we can form a category by taking the parts on the graph to be morphisms. But if there are weights, maybe there's a way to do the same thing with enriched category theory. And that might give some applications to these epidemiology models. So construct a free category on a directed graph with weights.
Yeah, so I think what you're doing now is moving into the next session where we will be doing the exploration of the questions. The purpose of this session is to give background on category theory that will be useful. So if you want to explain what an enriched category is, you're most welcome to do that.
Luca and Elena could do that.
But I don't think we will realistically manage to do that because we don't have a lot of time, and it's quite a technical concept. But it is an important concept because metric spaces are examples of enriched categories. So this is where instead of saying that for every two objects you've got arrows between them, you say that for every two objects you got something between them. This could be distance between the objects as well. And then the metric axiom, the triangular inequality, becomes an analog of this law. And the fact that distance between 2 points, between a point and itself is 0, becomes an analog of this law. All right.
Please ask questions, because whatever that question, a research question you are going to do after the lunch, one of the questions will be based on something related to this. So if anything is not clear to you, need further clarification, please feel free. Anything about graph side, about the category side, your own questions, please. Because if this is not clear, of course, research question will be more problematic. Feel free.
I'm going to leave you now for 1 hour, and maybe you can move to the next topic at 12 o'clock. Yeah.
Yeah, you'll be back before lunch.
Yeah. Where do you go for lunch?
After.
Yeah, I'll be back before that.
You are going for half an hour, right?
Yeah. Yeah. 12:30. No, you're right. Yeah, sorry. I will put vouchers on my way. On the WhatsApp group.
So we'll not start.
No. Good. Okay. See you soon.
Okay. Now, it does not work. Where should I put it? Here. Yeah, it should work. Yeah. Blue mark. Okay, so we wanted to understand metric space, semi-rings, and something. Do we all know the definition of a metric space? Yes or no? If you don't know, just say I don't know. No harm. Nobody is going to kill you. Do all of us know metric space? No, you are excused. Is it fine? Okay, good. Then I have a question on metric space. You tell me the answer, okay? So we start with a function. We generally write like D. How we write X? That's you prefer, right? Or what? X. Good. What do we write on the right hand side?
You can write the real number, you can write X.
You can write X on the right hand side.
Yeah.
That's why I asked, do you know the definition of a metric space? Yes. Positive real numbers. So he said positive real numbers. Positive means including 0 or excluding 0? Including 0. So it's not positive, it's non-negative. They are very big difference. Something like this way. Then he said, I can also write X. Any other suggestion? Yes.
0 to infinity.
0 to infinity, including 0 or excluding 0?
0.
Including 0. So this is your first choice, this is your second choice. Should I include infinity or not include infinity?
Exclude it.
Exclude infinity. Okay, good. Any other choice?
Want to include infinity as well.
You wanted to include infinity. Okay. Of course, we need to understand metric space before we go work on a project, right? So we need to know the definition first. Are we all? Any other suggestion for metric space? The codomain. Good complex numbers. Okay. Any other? Huh? Integers. Remember, whatever you suggest, you have to justify me that it will be a metric space. It's not the random gambling we are doing. Whatever you propose, you have to satisfy those three axioms, what has been written yesterday. That's your responsibility. It is not my responsibility. Okay, so you said integers. Okay.
You just put real numbers.
Okay, that's your problem. I am not saying anything.
Okay.
I just wanted to understand which of these candidates can win the vote with respect to metric space, because we need to understand what is a metric space. Okay, any other suggestion? Don't randomly bring somebody from the shop, right? You have to literally justify your actions. You know these three actions, right? Okay, let's go one by one. Which one of them is absolutely impossible to justify those actions? Which one of these, this question is only for students, of course, is absolutely impossible or rather nonsense to justify? Yes.
Those interval of 0 and infinity.
Is it bad? Really? Do you think this is bad?
The what?
Or this one is bad? Oh, so he's bad. Okay. Okay, so he's bad. Okay. Bad is not enough. Who is absolutely useless? I mean, which one is we cannot do? We have many choices. You said which one is absolutely no way we can do that for metric space checking. Do you see there is one person is absolutely impossible? Yes.
I think it's X because
I think it's X. Do you see why?
you're saying the distance between points on X and points on X is X. The whole space.
It will not make sense, right? How we do those things. Okay, so let us write those three actions. Okay, you tell me what are those actions?
Equals to 0.
The distance between 2 points is equal to 0 or greater than 0. Very good. Next. Distance between 2 points is equal to 0 if and only if they are same points. Good. Number 3. What do you mean by that?
That's from X to Y is the same as the distance from X.
Right. Distance from X to Y is the same as distance from Y to X. Anybody else? What do you mean by that?
Between X and Y
X and Y
is less than or equal
less than or equal to
in X and Z.
X and Z. That's distance between Y and Z. Does it matter whether I write XY here or XZ here or YZ here? Does it matter? They think it don't matter. What do you think? Does it matter? Instead of writing this, if I start with XZ and put this other, doesn't matter. What I'm saying, He suggested this. I'm saying I don't like him. And I wanted to write this. Am I right? No? The same?
Yeah, you can write it.
Can write it and are these two same? Are these two same? Can I replace this by this? Or replace this by this? Or one has more value?
But say you can if only if you're keep the same motion throughout.
No, I'm saying as number fourth axiom, instead of writing this, can I write this? He proposed this. I'm saying I don't like his proposition, I want this. Can I do that? Can I do that?
I don't think so. I don't.
You don't think so?
Yeah.
Okay. Mhm.
Because if you draw points,
Ah,
and there, I think.
it will be different. You think so? Okay. What do you think? You think same, okay? And you, what do you think?
I'm saying you're taking it exactly from the one above.
These all are same.
Yes, no, I'm saying
Yeah.
the distance between X and Y, right? Is less than equals to the distance between X and Z plus the distance between Y and Z.
Right.
So are you choosing that one?
I'm removing this whole statement by this bottom one. Can I do that?
You are removing the whole statement.
Yeah.
Then you are taking the one off.
The bottom, what is it in?
I'm not sure if you are understanding it. What I'm saying is.
This is one statement. This is another statement. I can write another one, third one. Just choose which one is not here. The X, Y, X, Z and Y, Z, right? So we can do this. So there are three ways to the permutation combination of these people, right? Can we choose any one of these? Or does it really matter? I have to choose this or I have to choose this. I can't choose any one of them. Yeah.
I think you can choose.
You think I can choose? He thinks I have to fix the first one or the second one. You said first one. Okay. And what do you think?
I think that's why I was asking if directly from the second one, right? So the thing is, the way I understand the triangle inequalities in relation to the points. So obviously, if it satisfies from above within the same points.
No, these are for all XYZs.
XY only.
All XYZs. Any XYZ. I mean, whatever written is everybody from here. When I'm applying this, it's not fixed with some, only I'm taking some 1, 2, 3, 4. Everybody is allowed to follow this rule. Yes.
We can even further verify this.
Verify this. What do you think?
The distance between me and you, then that's the distance between you and me, right? Hence, I'm saying it doesn't really matter if you start with the Y or the X.
No, the distance between you and me and you is already covered there. Where is it? Number 3. So the question, there is no problem with number 3. Nobody objected it. But what about number 4?
Quality.
Yes.
The distance between X and Z is the same as the distance between.
But that does not explain which one should I take. Question is, somebody want this, somebody want this, somebody want this. Are these all equivalent? Doesn't matter which one we take, or it is really matters exactly one of them should be there, others shouldn't be there. So you think, okay. You think it doesn't matter? What do you think? Doesn't matter, right? I can write any one of them. Okay. You said you also think doesn't matter. You still think it does matter.
Because the points are from.
No, set is fixed. X is fixed. Okay. And what do you think?
It doesn't make sense to me.
So you don't need to look at him. You have your own ideas and you are feel free to express whatever you think, just express, because we are here not to do performance or to show somebody that we wanted to clear it up. Whatever the things is cluttered up in our mind, we have to understand it 100%. If you understand something 99%, this is absolutely nonsense, useless. It should be 100% or nothing, nothing in between. Okay, so feel free. What do you think?
It does matter.
That matters. Good. Stick with your decisions until you change it with a good reason. What do you think? It does matter. Okay. What do you think?
I also think it does matter.
It does matter. You cannot just pick anybody randomly. There is only one is the right candidate. What do you think? Doesn't matter. You see, Maggie? And some of you are already working on metric spaces, right? Okay, who is working on metric spaces? You. You are not.
Yeah, I could say this because I'm working on a little bit space, so there is the distance now.
Of course, you have metric space, right? Hilbert cannot survive with metric. Okay, who else working on metric spaces? No. You working on what? Graphs. You?
Lie symmetry.
Lie symmetry. You? Lie symmetry. You? Graphs. You? Graphs. Okay. So I cannot conclude what I wanted to conclude because it looks interesting. When we have this kind of problem, okay, so do you understand this is not a voting system, right? So if there are more people saying this doesn't matter, less people, I don't like, this is another party, opposition party, it's not like that, right? It's mathematics. Yeah, majority says something, that is why it is right. Mathematics is not neither a dictatorship nor democracy. None of them is true, mathematics. Mathematics is mathematics. And if it is true yesterday, it will be true today, and it will be true 1,000 years from now on, if we still exist. Okay. So the question is, you can have a doubt like this. You may not be sure whether which one should we take, it doesn't matter, or it really matters. That is a very natural question. How to solve it? That's a question. I have a doubt. It is natural, because if you don't have a doubt, then that's a more problem. If you just blindly follow something written in the book and that's why it is true, don't take it, because half of these textbooks, what you follow is complete nonsense. Complete nonsense. They even don't understand. Those are not written by mathematicians even. Like the Stewart calculus. It's an idiot completely. I can prove it. So when you have a doubt, how to fix it? That's all about doing mathematics. Whether doing research in pure mathematics, applied mathematics, that's not the problem. This is also a research problem. To you. So you three had doubts, right? How to fix it?
Maybe we can try to, since you're dealing with a triangle, right?
Yes.
Let's try to demonstrate it and
demonstrate.
Yes.
Good. So let's draw some pictures, maybe. Looks like I will not be able to go to seminar. So now we understand, right? Because these D's are, I actually draw almost an equilateral triangle, which is bad in some sense, which is really bad. So each of these D of 2 means the length, something like that. Okay.
Yes. Yes.
Now let's just try to understand. dxy is this length. If we go back to high school, we have some geometry, right? Euclidean geometry. We have a triangle.
Yes.
And then we have 3 sides. Do you remember there was a theorem? Theorem.
Yes.
Pythagoras.
There was a Pythagoras theorem, and before that, there was a much simpler theorem. that the sum of these two is bigger than the third one for any triangle. There was such theorem. Did you come across such theorem? If I give you any triangle, not rectangular triangle, not Pythagoras even. Pythagoras is nice. It's very nice. It's even no inequality. It's equality even in a different way. But if I give you any triangle, the sum of these two sides is bigger than the third one. Have you came across of that? Yes or no?
Yes.
If not, no problem. Let's go to the real world. You like applications, right? Let's, immediately move to this. Real world now. Okay? Imagine here is an ant. Ant. Okay? And I put a sugar cube here on that Y. Okay? Now I'm sure you agree, ant never study function analysis. Do you agree? Never study Euclidean geometry. Do you think that to eat this, the ant will go like this and this, or ant will go like this way?
I should test.
Which way ant will prefer? If he has only two ways to reach the sugar cube, which way ant will go? I'm sure ant is not so idiot to go from here to here and then go there, right? Even ant is so intelligent that it will go from X to Y. Done. Do you see why ant will go from X to this way, not this way?
Yes.
He has to travel more. If I have to go from here to Cape Town, of course I will not go from here to Pretoria and then Pretoria to Cape Town, right? Anybody understand this? So this triangular inequality does not need a university level of thinking to understand. Even an ant can understand that. Ant does no triangular inequality without knowing metric space. Do you see the point?
Yes.
Now, does that answer three of your doubts? At least you are all convinced all of them are true in a triangle. Do you agree?
Yes.
Because of this reason. That's you agree, right? Okay, so in a concrete situation, this is true. But now if you swap between this X, Y, Z, I just randomly move it, taking the same idea. Now are you convinced, like your other fellows, that it does not matter which I am writing? Whether I put ant here, or ant here, or ant here, and put the sugar in any other places, will it make any difference? No. Doesn't matter, right? Whether I put my ant here and sugar here, it will be the same situation, right? Whether I put my ant here and sugar here, it will be only the three possibilities are there, right? Between these two. And that's exactly what we have three possibilities here, because there are 3 points. Convinced? Yes or no? He is 99.96%, right? You?
No, Prof. I'm like, then what if?
Tell me what
happens then if move the end to Y straight away, and then I don't move those sugar.
You don't know sugar?
Yes.
Oh, then that's a different actions. If ant and sugar in the same place, then you already captured it, right? dxy is equal to 0 if ant and sugar in the same place. So we already covered. Exactly, that's a good question. That already covered by that action. Okay, now are you convinced 100% or it is now 99.9994?
I think I am. it makes sense.
100%. Are you sure? No. Please clear it. Please clear it. That little bit doubt will be an atom bomb. It's a very bad. No doubt should be there in your mind. Like 2 plus 3 is 5. Do you doubt?
No, I don't.
No. Do you doubt?
No, I don't.
No. It's 100%, right? So this thing should be just like 2 plus 3 is equal to 5. If it's not, then you didn't understand it. So make it 100% here. Yep.
You know where the confusion was? The idea that X, Y is less than the idea, yeah, it makes sense. But you know, I think the confusion was we literally thought distance from X to Y was literally equal to distance from X to Z. And then it was literally equals to distance Y to Z.
Right.
I think
So you were fixing the points.
Yeah.
That was the problem. Then you were thinking, if I fix the points, how can I change the things?
Yeah.
But these all axioms are happening for all these things. Why? Remember, what was the definition of a function? Function was saying I have to take everybody, right? So I cannot fix only some people and not take other people. So you see, if you
to X, Y, it applies to X, Z.
Exactly. If we do not understand the definition of a function properly, or if we would have understood the definition of a function properly, then you wouldn't fix your mind with only 3 points. Because then you know by definition of a function, I have to vary everybody. Everybody should go in the domain because X is in the domain of the function D. Clear? Are you 100% now, right?
Yes.
Okay. Good. So it does not matter. So now we know what is a metric space. Now let's go to, okay. Oh, didn't fix this one, right? This one. Oh, this is more problem now. Okay. Okay, so at least we understood this is a problem, right? Why? Because, do you see? We wrote something 0. If we write X here, who is 0? It's a set. Do you see? If I write X, it is a complete disaster because there is no 0 in X, right? X can be anything. All universities in South Africa, where is 0? Here. 0 is a really bad person. I mean, X is really. Who else is also bad? Who else is also bad? So one problem is solved, but we have to still figure out who are the bad people. So they picked out X is bad. Okay. Who is also bad, or rather impossible to satisfy these equations? Yep.
0 to infinity.
Including infinity. So he is bad. Okay. You have to clean your record that you are not a criminal. This is your court. Tell.
Why do you think?
So he will be clean and he will not go to the jail if he can prove, including infinity, all these holes, right? Then you have no objection. Am I right? Why not? Because we say, I will allow everybody here who satisfy all these, right?
But he didn't.
No, yeah.
He just answered him.
No, he cannot clean. X was his suggestion.
Let me clean myself.
Oh, he should go to jail, right? Yeah, he go to jail. Yeah, okay, so he's a criminal from that point of view. Okay. But you understood why X cannot be there, right? Because we have zeros. Okay. Now, do you think that if you include infinity, we cannot get all of them, or one of them is a problem?
I will get all of them, but
you remember, when you do calculus, we do over reals. But sometimes in some good books also includes 2 more animals, minus infinity and plus infinity. Do you remember in some books, if you read good books? And then they tell how it interact with the real numbers. Like if you have a real number R
and if I add infinity. There is a formula for that. There is a definition for that rather. Because R is a real number, infinity of course is not a real number. It's just, by the way, infinity is not a real number. Do you know that? Yes. Minus infinity also not a real number. Just a notation. Think like just a notation. I can write cat, bat, rat, doesn't matter. Okay? So in some good books, they said we define it in some way. How they defined it? Do you remember or have you seen that? If I add infinity with any real number, what will get? Infinity. Good. Good. And if I have multiply with infinity? Infinity. Infinity. Good. And if I divide by infinity? Zero. Wow. Fantastic. Okay. But infinity. Huh? R is any real number.
Undefined. It's a real number, right?
Yes. It's any real number.
Infinity divided by.
If it's in a real number, it's
any real number.
Undefined infinite.
Who will be the problem? R can be 0, right? Is a real number. So whatever your answer will be, that should also consider that special case.
If R is any real number.
R is a real number. Of course, R will not be infinity because it's a real number. But if it is 0, then infinity by 0? Yeah. Okay, Dr. Mesiti, it was your child, so you have to.
I noticed that I don't need multiplication, I don't need division to write the 4 axioms.
So which one you need?
I'm happy to just use the first there, R plus infinity equals infinity.
He said, I don't need to argue for an hour, only 5 minutes is sufficient because he only need to satisfy these axioms, right? And he claims only knowing this definition, he can.
I add one more.
Okay.
Infinity plus infinity equals infinity.
You want also this. So if you allow him to bring these to witness, then he can prove he is innocent. No, he only want this and this. R plus infinity. Which one?
Good afternoon from online.
Good afternoon.
Oh, sorry to disturb. Because I'm not seeing on the screen, I'm just trying to follow just mentally. So now I want to ask, does this also relate to Jonas' game theory of the prisoner's dilemma?
I'm lost.
Because I was just listening, trying to figure out what is happening on the screen. And so I was just asking that what you're talking about, does it relate to Jonas' game theory?
No. It's just full metric spaces.
Okay.
Okay. So
okay, thank you.
Mesiti wants only these 2 extra conditions to be satisfied to include infinity. Do all of you agree that he will be able to prove all of this? Yes or no? It depends.
On the definition of B.
On the definition, of course, we keep any set X.
Yeah.
Now she is countering you. She is saying it depends which X I am choosing here. What do you think?
I think Elena.
For any set X, can you prove all these 4 axioms allowing you to do only these two rules, along with, of course, real numbers.
Some functions D will be metric, the other ones will not.
Will not.
Is the yeah. No, but I'm just saying I can do whatever you want to do with real numbers greater than 0 without infinity. I can do it also with infinity included.
But you can't do it for any metric space, right? Can you satisfy these 4 axioms for any set X, considering your codomain including infinity?
Repeat the question.
The question is, instead of taking this one, which we generally write, can we write this for defining metric space?
We are asking if there's a way to take a metric space and extend D.
Yeah, extend this, yes.
Yes.
So you can prove all these axioms.
Raise your hand.
Yeah.
I don't think it is possible to prove it with the 0 included to infinity. But for me, I only have a challenge with the integers.
No, let us first clean him before we go to integers. Yeah.
I also want to clean myself.
Yeah.
I don't understand why. I guess, let's say, assume that X is in point X. Not, I don't want to use the real numbers. Let's say the distance from here to here is A.
What do you mean by that?
So what if A is inside the X?
Yes, that's exactly. We are trying to measure the distance between these two.
Why are you okay, sir? Firstly, I want to understand why are you against my X?
Against your X. You see, we say these will be our axioms. And D is a function from this to something. And you proposed on the right-hand side X. Okay?
Yes.
But one of these two axioms as an image contains something like this, which is 0. 0 as a real number.
And it does satisfy.
Does 0 here? Does 0 here?
Yeah, it satisfies the properties.
No. I'm asking, as an element of this set X, is 0 here?
Yes.
Really?
It does satisfy.
What does X bigger than or equal to 0 mean?
Meaning the distance between.
No distance. Okay, so you have a problem with the function. When we write dxy and we write 0, do you understand that this thing is not anymore on this side? It's something we are associating a real number. So this is a real number which is 0. Is it clear?
Yeah, I doesn't make sense to me.
Is 0 is a real number, is it clear?
Yes.
Okay. D is a function, is it clear? The domain of the function is an arbitrary product of same sets, is it clear? And when we write 0, do you understand that it's the image of some point from the product to this side, is it clear? And if the image is 0, is that 0 is in X cross X or in X? Is it? How? X is an arbitrary set. How you get 0? 0 only can be in some real number. 0 can only belong to when X is equal to R, then 0 can be here. But our X is any arbitrary set. How can 0 be here when X is not real number? Okay, so we need to clarify these things. So there is a much bigger problem now. Okay, but
So take X, the set of the people in this room, ourselves here in this room. Then, of course, you can say a distance between me and you can measure a number of centimeters, and you define D like that.
Okay, let's say we are trying to measure a self-distance.
Distance, okay. So I am X, he is Y.
Self-distance.
Set distance. No, there is no set distance.
Self.
Safe distance. Okay. We are in COVID-19, say COVID-25. And we want 5 meter distance. Okay.
No, self-distance.
What?
What is self-distance?
Self-distance. Yes, yes, self-distance, right. Do you agree self-distance is 0?
Self-distance, distance between you. There's no distance.
So what is that?
Zero. And meaning it satisfies this property.
Right.
So 0 is included in that X.
How?
I'm trying to measure the distance between you. So meaning there's no distance now. Because I can't measure.
But the set X is the set of people, right? So if now D goes into X, it means that the distance between me and you is a person. So you're saying the distance between me and you is Prof. Goswami. Or the distance between me and you is you.
Yeah, we have to go out.
Okay. I want to understand what does that mean for this exo.
What does it mean?
Yeah.
Okay, it means, okay, we don't have time, we have to go for food. It means if dx equal to 0, then x equal to y. Okay?
Yes.
It also means and if x equal to y, then dxy equal to 0. So this whole thing has been replaced by this more fancy way of writing. These two facts together, replaced in a fancy way, we wrote it. Clear?
But now let's assume the distance between me and you are equal. And
What do you mean by that equal? That does not make sense.
This is what exam is meaning, the exam 2.
What do you mean by distance equal?
So when you're saying your set X is 0, that's what you say.
Yes, 0 is included. Must be included.
So the whole set, like X is equals to 0. The set X for you is 0. I don't. Is it your point?
Okay, let's go for lunch because
We are here. Yeah, it means there's no distance, didn't move anything. Right? Yeah. Doesn't mean that in this club there is no. Yes, there's a
it's everyone.
So basically, you say you take the end to y, and the x equals to y. Ignore the that doesn't mean 0.
Hey, that doesn't mean yeah. That's the point. That's the thing. Hey.
Site of something. Site is a colon of area.
Distance might be a number. What does distance mean equal? So me and we are hard. What do you say?
Okay. To measure the screaming, the taking the distance.
It's the difference between two things.
Monday or Tuesday.
Yeah, I come on Tuesday. We are not writing Monday.
Yeah.
It's not.
Okay, so we'll break for lunch now and resume at 2. So I'll stop the Zoom for now, and at 2 it will restart.